Okay, so in this video, we are going to look at basically the second way for you to be able to calculate a theoretical delta H for a reaction. Okay, the first way was the one we looked at in the last video where we looked at additivity method. Okay, the other way to calculate it is to use what we call standard molar enthalpies of formation. So standard molar enthalpies of formation basically tell us how much energy is involved in forming 1 mole of a compound. So you have a page, or 2 pages, I guess I should say, in your data booklet that contains all of this information for you. Okay, so if you go to your data booklet, these are the same pages that you've actually always used to figure out the name and the formula for things you got stuck on. Okay, you'll notice this table is called Standard Molar Enthalpies of Formation at 298.15 Kelvin. And so what you probably never looked at before, though, was this last column. So what this last column gives you is what is the heat of formation for each one of these. So what this is telling me, if I look at aluminum oxide, is if I wanted to make 1 mole of Al2O3 from aluminum and oxygen, I would need, or actually I wouldn't need, I would be releasing 1,675.7 kilojoules for every mole that I produced, right? So when you look at these heats of formation, you'll notice some are negative and some are positive. It really depends. There's no set stone rule that all heats of formation are exothermic or all heats of formation are endothermic. There really isn't, right? It comes down to we have to break the bonds holding the reactants together to form the bonds of the products. It takes energy to do that, okay? So generally you're going to know that you need to use heats of formation because the question is going to give you nothing. It's not going to give you a series of equations. It's not going to give you calorimetry data. It's just going to give you an equation potentially and say, what's the delta H for this? At which point you need to come to this table and pull these values. Okay, you'll notice when you look at this table, there are no elements on here. And that's because we don't write formation reactions for elements, right? Formations are for compounds. So we assume that the heat of formation for any element is 0. Okay, so if you needed to use that in your equation, you would use 0 for an element. Okay, so going back to here. Okay, normally I would spend a little bit of time talking about decomposition because decomposition relates to thermal stability, right? You have that data table full of formation reactions. A decomp is the opposite. So to do the opposite, all you would have to do is flip the sign of that delta H, okay? I'm not going to go into this too much because we are not going to ask you about that this year. But yeah, if you were writing a diploma, you would want to make sure that you kind of read that and make sure that you understand it. But no one's writing a diploma this year, so you're good to go. Okay, so here is basically what the equation for Hess's law looks like, okay? So we have that delta RH naught, and we use R because most of the time it's a random reaction, it's not a formation, and it's not a combustion. But if it was a combustion, I would put delta CH naught. Okay, these are all going to get naughts, and they're going to get the naught because I'm going to my data booklet to pull these values, and those are all standard values. So the delta H of my reaction is going to equal, this symbol here means the sum. So the sum of N delta FH naught of the products. So N is the number of moles that I balance my equation with. Okay, so if I balance something with a 2, I would put a 2, then I would look up the heat of formation for that particular compound in my data booklet, and I would multiply that by 2. So it's going to be the sum of the products minus the sum of N delta FH naught of the reactants. So biggest thing to remember is products first, then you are subtracting reactants, okay? So let's look at an example. So what is the enthalpy change for the following reaction? So I look at a question like this. I'm going to say, can I do a calorimetry calculation? No, I can't. I don't have any delta T's, I don't have any masses, I don't have any of that. Is this an additivity method question? Nope, I haven't been giving a series of reactions. At which point, the only thing I'm left with is for this to be a heats of formation. I'm going to go to my data booklet, I'm going to get this information. So looking at this equation, we're doing methane plus oxygen to give us carbon dioxide and water. So this is a combustion reaction. So when we start our equation, we are going to write delta Don't know why it's so hung up on going into superscript mode of late. So delta CH, okay, and a C, because this is a combustion reaction, it's not a generic reaction. So this is going to equal the sum of N delta FH naught of the product. So I look at my products. So how many CO2s do I have? I have 1. So I'm going to say 1 mole, and then I'm going to go to my data booklet and I'm going to find carbon dioxide. So CO2 is here. You'll notice they're all in alphabetical order. Carbon dioxide is negative 393.5. Okay, so we are going to do the 1 mole times negative 393.5 kilojoules per mole, because that's the heat of formation of carbon dioxide. Okay, then we are going to add, because it's the sum of the products, our other product. So we have 2 moles. Okay, we then need to go find water as a gas. Okay, I've been mentioning all through the unit, you have to be careful with water. The reason you have to be careful with water is, look here, it's in here twice. Once as a liquid and once as a vapor. So you have to make sure that you are pulling the right number, because look, they're different numbers. So we had water as a gas, so negative 241.8 is going to be the number that we need to pull. So negative 241.8 kilojoules per mole. Okay, so there's the sum of my products. From this, we need to subtract the sum of my reactants. And I'm actually just going to put this down a line so I don't run out of room. So reactant-wise, we have 1 mole of that methane. We're going to then go look up the heat of formation of methane. So methane is here. It's negative 74.6. So negative 74.6 kilojoules per mole. Okay, then we are going to add the 2 moles of the oxygen, but oxygen is an element, so it's going to be 0 kilojoules per mole. Okay, so the sum, which is why I put the big brackets around all of this, of N, which is the 1 mole and the 2 mole, delta FH naught of the products, right? So we did the products first, and then we are subtracting the reactants. So we've used this question quite a bit in our notes as we've worked through it, so you should potentially know that it should be coming up with negative 802.5, but if you don't remember that, that's okay, because we are about to calculate it. So type all this fun stuff in your calculator, making sure, sorry, I'm pointing at my screen, that doesn't help you, that you don't forget to put the big brackets around here and here, as well as here and here. Okay, the second set of brackets is the most important, because you need to subtract the sum of the reactants. And if you forget brackets around the whole thing, you're only going to subtract this, and you're not going to subtract that. And yes, I know in this case, this equals 0, so it doesn't matter, but not all questions are like that, okay? So I do this, and sure enough, the answer I get is negative 802.5 kilojoules. Okay, this is also a pretty common type of question that you will get asked. So this type of question will generally give you something that is not in your data booklet. And I know this isn't a great example of this because octane is in your data booklet. But I promise you, if you actually got a question like this, it would always be for something that is not in your data booklet. So just being like, oh, I'm going to go look it up in my red book isn't going to help you, okay? So this one says, determine the molar enthalpy of formation for octane. So we are trying to determine what the delta FH naught is. So like I said, normally a question like this, if you looked for octane in your data booklet, you wouldn't find it. In this particular question, you will, which is why I said it's not the best example, but it'll still work to kind of show you. And then because it is in your data booklet, you can check to make sure that you actually did it right. But again, normally a real question like this would not be in your data booklet, so that wouldn't really be an option to check. So it has given us the molar enthalpy of combustion. So this is where you really have to make sure that you are reading questions carefully, which is something that some of you guys do a great job of and some of you guys don't really do it. And I know I'm totally guilty of it too, right? Sometimes you skim the question and then you miss something important. So why this matters is knowing where you need to place things inside of your equation. So first off, we need to write the combustion of octane. So octane is C8H18. It's a liquid. Okay, plus oxygen to give us CO2 and water. Okay, balancing wise, here's another key piece. This gave me the molar enthalpy of combustion of octane. So I want to make sure that I keep this as a 1. Even if that means I have to balance as a fraction somewhere, that's okay. I need to keep that as a 1. So this is going to go in as an 8. This is going to go in as a 9. And so this is going to go in as 25 halves. Okay, because otherwise, I can't balance it with one of these, okay, right? Normally we'd be like, oh, we're going to double everything. We'd have 2, 16, 18, and 25. But in this case, we need to make sure that this stays as 1 because this value here is per mole. So it would be for 1. If I had balanced this with like a 2, a 25, a 16, and an 18, then this wouldn't be the right number. I would actually have to double that number to be able to do that. Okay, so in this case, when I set up my calculation, normally we're solving for the delta CH, but we already have that, right? It was given to us in the question. So what we have is that negative 5,074.1 kilojoules equals, and I'm going to get rid of the per mole because I already have this as per mole. So this is going to equal the sum of N delta FH, not of the products. So we're going to have 8 moles times the carbon dioxide, which is negative 393.5 kilojoules per mole, then plus 9 moles, right, times the water. Oh, what's water again? There's 2 waters. I never remember which one's what. So water is vapor, negative 241.8. Okay, so there are my products. And then, should we put that kind of bracket? We are going to say minus the sum of N delta FH naught of our reactants. So we're going to say 1 mole. And this is where, in this case, we're going to pretend we don't know what the heat of formation of this is. Now, we can't actually look it up in our data booklet because that is what this question is asking us to find. Okay, so we're just going to put in here delta FH naught, okay? And that's going to be what we are looking for, then plus 25 halves of a mole times 0. So now we're solving for this instead of for this, okay? That's why this question is different. The last question asked us to determine the delta CH. This one gave us the delta CH, but asked us to find the delta FH. So really important to read the question to make sure that you are solving for the right thing. A lot of the times you guys just always want to solve for this, and then you throw this number into here. But this says enthalpy of combustion. It doesn't say enthalpy of formation, so you have to make sure you are watching for that. All right, so we need to solve for this, right? So we already know what this number is. We can figure out what this is, and then we can rearrange to solve for that. So let's do 8 times negative 393.5 plus 9 times negative 241.8. So again, I'm going to write everything out because I tend to lose you guys if I don't. But if you're like, I don't want to, you don't have to. So we still have the negative 5,074.1 kilojoules. Okay, I got the sum of this here. It's negative 5,324.2 kilojoules. Okay, then if we figure what this is, right, 1 times delta FH naught is delta FH naught plus 0. So we're just going to have minus this. Okay, so we need to solve for this because currently it's minus. We're going to switch it to this side, which means this is going to move over to that side. So once we do that, we should be able to determine what this is by doing the negative 5,324.2 plus 5,074.1, which gives us negative 250.1 kilojoules, and that would be per mole. Okay, so, and that's because technically this would have the mole unit with it because we did do 1 mole times that. Sorry, I left that unit out. Okay, so If you check your data booklet, this does match up with what is actually in there for octene. But again, questions like this are usually going to give you something that is not found in your data booklet, so you can't actually go there to look for it, okay? Okay, so quantities of energy involved in different reaction types. You're going to find that we generally can order how much energy is involved in different types of reactions. So if we go from highest to lowest, what you are going to find is we can rank these reactions. So you are going to find that nuclear reactions always involve the largest or highest quantity of energy. Okay, you can generally recognize a nuclear reaction because you'll notice you have like symbols, right? So there'll be the hydrogen, but then you'll notice there's numbers in front of it, and it'll have like a 1 and a 1. Or you could have like helium, and that would have, try to click over to something that's kind of hidden under this thing. That's going to have a 4 and a 2. So when you see these weird little numbers, that's a nuclear reaction. Always involves the largest quantity of energy. Don't need to be able to calculate, just need to be able to recognize that it's always going to be the highest. Then we have our chemical reactions. These come next. If you had multiple ones, either it would give you the delta H and you could rank them based off of the quantity of the number, or if it didn't give you some and you had to calculate it, you could use heats of formation to calculate it, and then you could say this one's bigger, this one's smaller, and so you'd be able to come up with that ranking from there. The lowest is always just going to be a physical change, right? So that change of state, right? So if we're taking water, let's say from a liquid to a gas or something, that's going to involve the least. So nuclear has the largest quantity. Okay, and sometimes you guys get confused. You're like, well, but the sign, what's bigger, what's smaller? Generally, when we're talking about the amount of energy involved, we're just looking at the absolute value of the number. Okay, so nuclear reactions would have the largest, then it would be chemical, and then it would be physical. Okay, so you'll see as you work through your booklet, there's a couple, usually I think they're multiple choice or numeric questions that are inside of your booklet. And this is basically the ranking you want to follow. Okay, so next thing to look at is energy and efficiency. Okay, we often talk about efficiency when we talk about thermochemical reactions. And that's because efficiency is talking about how much energy actually went to doing what we wanted it to do versus how much went to some not useful thing, right? Think about using a barbecue, right? Yeah, some of that heat goes to heating my food, but a lot of the heat is wasted, right? It's going to heat the barbecue itself, it's heating the air around it. So when we are looking at percent efficiency, it's actually very similar to percent yield that you have seen before. Okay, it talks about energy output over energy input times 100. The energy output is basically how much energy actually went to doing what you wanted it to do. So you're going to calculate energy output from experimental data. Okay, so this is going to come from your experimental data, which is generally going to be those calorimetry questions that you get, okay? Which is why it says calculated using MC delta T. Your energy input is basically theoretically how much energy is inside of there that could have gone to doing what I wanted, right? So even though the equation is technically written as output over input times 100, it's also more or less saying that percent efficiency that's not what I meant to do, is equal to that experimental over theoretical times 100, right? Which when you think about it, is basically what that percent yield is. So it can be helpful for you to relate it to that because you should already be familiar with percent yield from last year so that it's not a whole brand new equation that you have to learn. So efficiency questions are really massive calculations, and that's because they're going to require you to use calorimetry data to calculate an experimental, and they're going to require you to use theoretical to calculate theoretical, right? So we're looking at doing calorimetry stuff, which was some of the stuff we did early in the unit, and then using those heat shift formation, which is stuff that we did later in the unit, right? So I don't want to say these questions cover almost the entire unit, but to an extent they do, okay? They really check to see where you're at with calculations and can you do all the different types of calculations that we look at. Okay, so let's have a look at this example. So it says propane, which is C3H8, is a commonly used barbecue fuel. What is the efficiency of the barbecue as a heating device if 5.10 grams of propane are required to change the temperature of 250 grams of water contained in a 500 gram stainless steel pot where they've given us the specific heat capacity from 25 degrees to 75 degrees? Okay, so we are going to have to calculate two things. We are going to have to calculate the experimental data. Okay, so we're going to have to calculate experimental. And we're going to do that using all the calorimetry. So when we look at this question, it says, if 5.10 grams of propane are required to change the temperature of 250 grams of water contained in a stainless steel pot. So this barbecue is basically a flame calorimeter. So I have to be able to recognize that when I'm doing a flame calorimeter, when I go to calculate that delta CH, which is what we're calculating now, I have to do the negative, right? Because we always do the negative. MC, oh, okay, close, delta T of the water plus the MC delta T, in this case, of that stainless steel pot, okay, because that's what I have. So I have to make sure that I remember that whenever water is contained in some type of metal container, that metal container is also going to absorb energy, right? And then I have to be able to get this per mole, okay? So that's kind of my setup for my equation that I'm going to have. So we're going to have that this is equal to negative, okay, remembering this should be in terms of kilojoules, so I'm going to make sure that I use all my masses here and here in terms of that. So mass of water, we had 250 grams, so 0.250 kilograms. Specific heat of water is 4.19 kilojoule per kilogram degrees C. Okay, delta T, we went from 25 to 75, so that's going to be 50. Okay, so there's the MC delta T of the water. Then we need to combine it with the MC delta T of that stainless steel pot. So 0.500 kilograms times 0.503 kilojoules per kilogram degrees C. Okay, the temperature change is going to be the same. So it is also going to be 50 degrees C. Oh, that was not a bracket. Okay. All right, so all of that is taking care of that first set of data. Let me just make that smaller to try to get it to all go across the screen. Of course, now all that spacing shows up. Okay, so there's the MC delta T of the water. There's the MC delta T of that stainless steel pot. Now what we need to introduce, I'm going to give myself a little more space to do this because I know I'm going to run out otherwise. We need to introduce the moles of the propane, okay? So we were told it was 5.10, but we're going to have to go get the molar mass for it, which is 44.11. So we're going to do times 44.11 grams, and that is going to be per mole. And then to get rid of grams, we are going to times by 1. I'm going to mess around with my font size again. This is where I wish the screen was just a hint bigger. 18. Get rid of the space. We'll make this work. There we go. So times 1 over, and then we're going to put the mass down here on the bottom, which was 5.10 grams. Squeeze that over as much as I can. Okay, so the grams now cancel. I look at all my other units, right? This kilograms cancels that. The degrees C's cancel over here. and kilograms, kilograms, and degree C and degree C. So I am left with kilojoules per mole. So let's actually calculate this to see what we get as our answer. Okay, and we should be getting negative 561.75, and that number keeps going. Okay, and that's going to be in kilojoules per mole. Okay, the reason we want to calculate this in terms of kilojoules per mole is we need to make sure that we go to calculate our percent yield, they're both in terms of kilojoules per mole, right? If I didn't have them calculated in the same way, then me calculating that percent efficiency would be completely different because it would be using different scores, right? So there's my experimental. I had to do a flame calorimetry calculation because this was a flame calorimeter. Okay, now we have to calculate that theoretical. Okay, we're going to get the theoretical using those heats of formation. So we are going to have to write our balanced chemical equation, right? Because we need a balanced chemical equation to be able to do that. So C3H8 gas plus O2 to give us CO2 gas and H2O gas. Okay, we need to balance it. We want to make sure that this stays as a 1 because this is per mole of propane. And we want to make sure that we stay within the same quantity. Okay, so this is going to get a 3 here. This is going to get a 4 here, which means this is going to get a 5. Okay, so now that we have all of that, we can go and calculate. I'm not sure why that pasted all the way up there. Let's see if it'll let me move it. Okay, so now we can go and calculate our delta C H for this, right? And we're going to use Hess's law. Remember, Hess's law was the sum of N delta FH naught of the products minus the sum of N delta FH naught of the reactants. So we're going to do the 3 moles of carbon dioxide times negative 393.5 kilojoules per mole. Then we are going to add the 4 moles times, I want to say it was negative 241.8, but let's just check. Water to vapor, yeah, negative 241.8 kilojoules per mole. Okay, then from that we are going to subtract the N delta FH naught of our reactants. So for the propane, we have 1 mole of it. Heat of formation of propane is negative 103.8 kilojoules per mole, and then plus the 5 moles times 0. Okay, so from here, we can calculate what that's going to be. So 3 times negative 393.5 plus 4 times negative 241.8, then minus 1 times that negative 103.8, and 5 times 0. So we come up with negative 2043.9 kilojoules. Okay, and that is going to be per mole, even though we're not writing per mole, because when we look at our equation, there is 1 mole of propane here, right? If this was balanced with a 2, I would have to make sure that I divided this by 2 before I went and plugged into my percent efficiency. Okay, but now that I have all of that, we can calculate our percent efficiency, right? Because it is going to equal the experimental. I'm just going to put it in as times 100 over that theoretical. Okay, so we got to make sure that we use the whole numbers in our calculator. So it's going to equal, what did we have? Negative 561.75, and that kept going. No, whoa, why did I write 1,000 here? That should definitely not be 1,000, should be 100. Sorry about that. Okay, so this is all going to be divided by the theoretical, which we calculated as 2043.9. And then obviously we have to times by 100. Okay, so make sure when you put this in your calculator, you use that whole number for that number. I know some of you like to, when you get an answer like that, you like to save it. Some of you also just look at what you have, doesn't really matter. So let's calculate this out. And we should be getting not that number because I clearly didn't type it into my calculator right. And now I just cleared that other number. Hold on 2 seconds. Okay, so you should be coming up with negative, or not negative, I don't know why I'm saying negative, probably because I'm looking up here, but those negatives canceled, 27.5%. I think we can have 3 significant digits. Look real quick at the question. Yeah, we can have 3 significant digits. Okay, so 27.5%. When you think about it, that's pretty awful percent efficiency, but you also should be aware that combustion reactions being used to do useful things often have huge percent errors or huge losses of energy because we lose a lot of energy to other things. Okay, so that's how you do a percent efficiency calculation. It involves you doing a theoretical as well as an experimental. So definitely a large chunk of calculations going into that type of question, okay? There are some diploma questions for you to try after this. Percent efficiency is definitely a newer thing to appear on the diploma, so I don't really have any examples of that. But I'm sure if you look online, you can probably find some additional practice pieces for you to try. But yeah, there's all kinds of different questions for you to look at in here as well as in your question booklet, okay?